Hello there, and welcome to the Dreamy Science Channel. Tonight, we'll be discovering some of the strangest objects in the universe. Despite what you might see when you look at the night sky, not all stars are the same, and some are so strange and unusual that they seem to defy the laws of physics. Most stars look steady from afar, little points of light scattered across the dark. But as we explore them more deeply, the vast differences begin to emerge. There are some that pulse like beating hearts, some that spin so fast they throw matter into space, and others that aren't really stars at all, but remnants of something far more ancient. Some live by feeding on companions, while others erupt without warning. And some are so dense, so magnetic, and so extreme that they seem to belong to another realm entirely. Tonight's journey is a slow passage through these stellar oddities, cosmic exceptions that reveal just how majestic the universe can be. The deeper astronomers look, the more mysteries they uncover. And hidden among those distant lights are objects that challenge what a star can be, how it can live, and how it can end. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here, one sleepy soul at a time. But for now, all you need to do is relax. Let your body soften, allow your eyes to grow heavy, and let your thoughts wander upward as we explore our remarkable cosmos together. Let's begin. When a massive star collapses after a supernova, its core can be crushed into a neutron star. The object left behind is tiny by stellar standards, often only about the size of a city. But the matter inside it is packed to an almost absurd degree. Gravity presses atoms so hard that electrons and protons are forced together, leaving behind a sphere made mostly of neutrons. The result is a density so extreme that ordinary comparisons start to fail. A spoonful brought to Earth would weigh billions of tons. It would not sit politely in the spoon, it would punch through the ground with catastrophic force. Yet this impossible object is real. Some neutron stars spin rapidly. Some flash like cosmic beacons. Some carry magnetic fields beyond anything we can reproduce. They are what remains when a star loses its struggle against its own gravity and becomes something stranger than almost anyone expects matter can be. First up, some stars look impossibly young. Some stars look impossibly young in places where all stars should be old. In ancient globular clusters, most stars formed around the same distant time. That means the brighter, heavier ones should have burned out long ago, leaving only older, dimmer survivors. Yet, scattered among these elderly populations are stars that shine hot and blue, as though they arrived late to the party. Astronomers call them blue stragglers because they lag behind the normal aging pattern of the cluster. They seem younger than their neighbors, but they are not truly young at all. Most likely, they were rejuvenated. In crowded star clusters, close encounters are common. Two stars can merge, or one can draw fresh fuel from a companion. That stolen or combined hydrogen lets it burn brighter again. A second life, hidden among ancient suns. This is the real summer star. Some rare stars are already shedding themselves into space before they die. Long before the final blast arrives, some of the most massive stars begin to come apart in full view of the universe. They cast off huge layers of gas through fierce winds and sudden eruptions, building glowing clouds around themselves while they are still alive. Wolf-Rayet stars do this with astonishing force. Luminous blue variables can do it in violent outbursts that briefly make them far brighter than usual. Eta Carinae is one of the most famous examples. In the 19th century, it erupted so dramatically that it became one of the brightest stars in the sky. Yet it survived. What we see now is a great expanding nebula made from material the star threw off itself. These stars are not waiting quietly for the end. They are rewriting their own surroundings first, filling space with the ingredients of future shockwaves, future dust, and future worlds. A few stars pulse with such precision they rival atomic clocks. Some dead stars become pulsars, spinning neutron stars that sweep beams of radio light across space. If one of those beams crosses Earth, astronomers detect a flash each time the star rotates. The remarkable part is not just the flashing, it is the regularity. Certain pulsars keep time with astonishing stability, so steady that over long periods they can rival the precision of atomic clocks. Millisecond pulsars are the masters of this. They spin hundreds of times each second, often after being sped up by matter falling in from a companion star. Once that process settles, they become extraordinary cosmic metronomes. Their timing is so exact that astronomers use networks of them to search for faint ripples in space-time itself. A collapsed star can become one of the finest timekeepers in the universe. Some rare stars spin so fast they fling their own matter outward. Most stars rotate, but a few take it to such an extreme that their equators are nearly at the breaking point. These are often called B-stars. They spin so rapidly that gas can be launched from the star's outer layers and spread into a flattened disk around it. The star is not exploding, it is simply turning with such speed that holding on to all its material becomes difficult. That spinning disk changes the light we receive, which is one reason these stars look so unusual through a telescope. Their shapes may also be distorted, with the equator bulging outward while the poles remain hotter and brighter. In a sense, they are stars living on the edge of balance. Rotation becomes destiny. It alters their appearance, their behavior, and sometimes their fate, turning them into restless objects, half star and half storm, wrapped in matter they could not quite keep. There are stars surrounded by shells they cast into space themselves. Some stars end their ordinary lives, not with a giant supernova, but with a softer kind of grandeur. After swelling into red giants, they begin to lose their outer layers, which drift away into space. The hot core left behind lights the escaping gas from within, turning it into a glowing shell that can look like a ring, an eye, or a ghostly bubble. Despite the name, a planetary nebula has nothing to do with planets. It is the discarded atmosphere of a dying star, briefly illuminated before it fades into the dark. What makes these objects so captivating is their variety. Some are round. Some are bipolar. Some twist into elegant patterns shaped by magnetic fields or hidden companion stars. In the middle sits the exposed remnant, on its way to becoming a white dwarf. The star survives for a while, but only after casting off the very layers that once made it shine. In some binary systems, one star begins to age and swell until its outer gas drifts too close to its partner. Then gravity takes over, and the companion starts pulling that material away. What follows can be one of the most dramatic relationships in astronomy. A white dwarf can gather stolen gas into a hot, swirling disk before it crashes onto the surface. A neutron star can do the same, but with even more violence, producing fierce X-ray light. In some systems, the donor star is slowly stripped over time, losing mass to the more compact object beside it. These are not peaceful pairs. They are cosmic feeding arrangements shaped by proximity and gravity. Sometimes the theft triggers flashes, eruptions, or repeating outbursts. Sometimes it changes the future of both stars completely. A rare star in such a system is often not unusual because of what it was born as, but because of what its neighbor forced it to become. Not every star we see still wears its original outer layers. In close binary systems, one star can lose its hydrogen envelope to a nearby companion, leaving behind a much smaller and hotter object that would otherwise remain hidden. What is left is often called a stripped star, or a helium star, because the deeper layers are suddenly exposed. These objects are fascinating because they reveal the interior of a star before the usual final collapse. It is like seeing the glowing engine after the casing has been torn away. They can be difficult to detect because the companion may outshine them in ordinary light, yet their heat and spectra give them away. They may also be important ancestors of certain supernovae and compact remnants. A star does not always need to die to reveal its core. Sometimes a partner uncovers it early. Some of the strangest stars may be halfway between star and explosion. Astronomers have found rare outbursts that look at first like supernovae, yet the star seems to survive. These events are often called supernova imposters, a wonderful name because it captures the drama exactly. The eruption can become dazzlingly bright and hurl huge amounts of gas into space, but the core is not destroyed. Eta Carinae likely did something like this in the 19th century. For a while it blazed with astonishing intensity, then dimmed again, leaving behind an immense cloud instead of a dead remnant. They suggest that some massive stars can lurch toward disaster in steps, shedding mass in giant fits before the true ending arrives. The universe gives us a strange intermediate state, not calm life, not full death, but a violent rehearsal that looks alarmingly close to the real thing. Rare stars reveal that the universe makes far stranger suns than ours. Our sun is wonderful, but in stellar terms, it is reassuringly ordinary. Rare stars show just how small a slice of possibility that really is. The universe can make stars that pulse, stars that cannibalize neighbors, stars stripped to their cores, stars wrapped in their own discarded layers, and dead stars denser than anything our everyday minds are built to imagine. More importantly, these objects are not merely curiosities. They help explain where heavy elements come from, how binary systems reshape stellar lives, and how extreme gravity, magnetism, and pressure behave in nature. The strangest stars are often the most revealing because they push physics into unusual territory, exposing hidden processes that ordinary stars keep quiet. Once you begin to notice them, the sky changes. It stops looking like a field of similar lights and starts feeling like a place full of wild exceptions. These are among the most intense stars the universe can make. They began as very massive stars, but now they are in a late and ferocious stage where their surfaces are blasting outward in supersonic winds. Those winds are so powerful that they peel away matter at extraordinary rates, exposing deeper fusion layers that ordinary stars keep hidden. They are blisteringly hot, often far hotter than the sun, and they waste very little time. A star that massive lives on borrowed time from the beginning, and this stage makes that urgency visible. It is all burn and no patience. These stars can carve glowing cavities in surrounding gas and flood their neighborhoods with harsh radiation. When one appears, astronomers are often looking at a star already racing toward one of the most violent endings in nature. A magnetar is a type of neutron star whose magnetic field is so overwhelming that it pushes physics into territory that feels unreal. It can twist the star's crust, stress the surrounding space, and unleash sudden flashes of energy that sweep across the galaxy. In rare giant flares, a brief outburst can release more energy than the sun produces across a vast stretch of time. The field itself is hard to picture because nothing in daily life prepares you for it. It is not simply strong, it is monstrous. It can dominate everything nearby and alter the behavior of matter in ways we cannot reproduce on Earth. These stars are not just exotic leftovers, they are natural laboratories for the most extreme magnetism in the cosmos, and they remind us how savage a dead star can become. Pulsars are dead stars that sweep space with beams like lighthouses. When a massive star dies and leaves behind a neutron star, the story does not always end in silence. If that remnant is spinning and has its magnetic axis tilted away from its rotation axis, it can send out narrow beams of radiation that sweep through space like a cosmic lighthouse. Each time one of those beams crosses Earth, astronomers detect a pulse. That is why pulsars seem to blink. They are not flashing on and off, they are spinning with astonishing regularity. Some rotate once a second. Others whirl many times in the blink of an eye. These objects were discovered through radio signals, and at first, the precision seemed so strange that a few scientists wondered if it might be artificial. It was not. Nature had simply built something more exact and eerie than anyone expected. A pulsar is the soundless rhythm of stellar death turned into a beacon, steady enough to map the invisible structure of space. White dwarfs are stellar cores left glowing after ordinary stars collapse. When a star like the Sun runs out of fuel for its final stages of ordinary fusion, it does not explode as a supernova. Instead, it sheds its outer layers and leaves behind a hot, compact core, dense and brilliant at first, which slowly cools over immense spans of time. That remnant is a white dwarf. It is no longer generating energy through the usual stellar engine, yet it still shines because of stored heat. What makes it extraordinary is the balance holding it up. Instead of ordinary pressure from hot gas, the object is supported by a quantum rule that stops electrons from being squeezed into the same state. That strange resistance keeps the star from collapsing further, even though the whole object is roughly Earth-sized. Here is a stellar ember, tiny by stellar standards, but carrying the mass of the star's heart, one of astronomy's most elegant endings. Take the mass of the Sun, then imagine forcing it into something only about 20 kilometers across. The result is a neutron star, one of the most extreme objects nature allows without making a black hole. Its gravity is fierce. Its surface is compact beyond anything ordinary language handles well. If you stood nearby, the difference in gravity between your head and your feet would be catastrophic. In that remnant, matter is packed so tightly that the familiar structure of atoms no longer survives in the usual way. These stars can spin rapidly, emit radiation, quake, flare, and distort nearby space. They are tiny on the map of the cosmos, but in terms of physical extremes, they are among its most astonishing masterpieces. Some aging red giants change their chemistry in a dramatic way. Deep inside, fusion and mixing processes can bring carbon from the interior up into the outer layers. Once carbon becomes more abundant than oxygen, the whole atmosphere changes character. New molecules form, the star's light turns richly red, and carbon dust begins to condense in the surrounding gas. Over time, that dust can grow so thick that the star hides behind its own debris, dimming invisible light while glowing more strongly in infrared. The star becomes both actor and curtain, making the material that later obscures it. These objects are also important because they seed interstellar space with carbon-rich dust, the raw material for future stars, planets, and chemistry. A fading old giant is also a manufacturer of cosmic ingredients, quietly filling space with the stuff of future worlds. Not every sudden brightening in the sky comes from a star generating more energy in its own core. In some binary systems, the spectacle comes from stolen matter. Gas from one star spirals toward a compact companion and forms a hot accretion disk where friction and gravity turn infalling material into intense light. The feeding itself becomes the engine of brightness. Cataclysmic variables are a classic example. A white dwarf gathers gas from a nearby donor star, and the disk can suddenly flare when conditions change. What makes these objects so gripping is that their brightness is not self-contained. It is the visible sign of a relationship, often an unequal and destructive one. One star loses, the other blazes. When astronomers watch such a system brighten, they are witnessing not a solitary transformation, but an ongoing act of cosmic dependence and theft. Rao Coronae Borealis stars can vanish behind clouds of their own carbon. Most variable stars change brightness in some predictable rhythm. These do something stranger. For long periods, they may shine steadily. Then, without warning, they plunge in brightness, as though someone has pulled a curtain across them. The star itself has not gone away. Instead, it has formed a fresh cloud of carbon dust that drifts into our line of sight and blocks the light. Over time, that dust disperses and the star brightens again. The effect can be dramatic, like a celestial disappearance act performed by the star's own atmosphere. These objects are rare and deeply mysterious. Some may be merger products born when two white dwarfs combined. What makes them unforgettable is the sheer theatrical quality of their behavior. A star can spend years glowing normally, then suddenly hide behind matter it just created. Even old stars can still surprise the sky. 104 Zhitko objects may hide a neutron star inside a giant. This idea sounds like something invented for science fiction, yet it comes from serious astrophysics. A Thorm-Zhitko object would form if a neutron star ended up inside a red supergiant, settling into the core rather than destroying the whole star outright. From the outside, it might look almost ordinary, just another swollen giant star. But deep inside, the engine would be bizarre beyond comparison. Instead of a normal stellar core, there would be a collapsed neutron star, altering the structure and driving unusual nuclear processes. That could create strange surface chemistry, which is one of the few clues astronomers can search for. A few candidates have been proposed, though none has been confirmed beyond doubt. What makes this concept irresistible is its disguise. The most bizarre stars may not always look bizarre. One of the oddest objects in the universe could appear, at first glance, like a familiar red giant, while hiding an impossible secret at its center. Luminous blue variables can erupt without actually becoming supernovae. These are among the most unstable massive stars known, brilliant, hot, and living close to the limits of what a star can bear. At times, they become dramatically brighter and can throw huge amounts of gas into space. Yet, they survive the event. That is what makes them so fascinating. The eruption can look almost like a final catastrophe, but it turns out to be a violent episode rather than the end. Eta Carinae is the iconic example. Its 19th century outburst was so intense that it briefly ranked among the brightest stars in the sky, and the material it expelled still forms a vast glowing nebula today. These stars seem to live in a state of barely controlled instability, forever on the edge of becoming too luminous for their own outer layers to hold. They convulse, shed, recover, and remain in view. Each eruption a warning that something larger may still be coming. It emerges through struggle. Inside dark clouds, gravity draws gas and dust inward until a protostar begins to form, often surrounded by a disk and tangled magnetic fields. During this stage, the light can vary in irregular and fascinating ways. Material falling onto the growing star may arrive in bursts, making it brighten suddenly. Dust in the disk can drift across our line of sight and cause dips. Jets and hotspots can alter the signal again. When astronomers watch certain young stars flicker, They are not seeing a stable star misbehaving, they are witnessing an unfinished object still negotiating its own creation. The process can take millions of years, and planets may be forming in the surrounding disk at the same time. The flickering is part of a larger story, not just of stellar birth, but of the chaotic environment from which whole planetary systems eventually emerge. Others shine strangely because two stars have merged into one. Sometimes the explanation for an odd star is not that it was born unusual, but that it became a single object through collision or merger. In close binary systems, orbital decay can slowly bring stars together until they coalesce. In dense clusters, direct collisions can also happen. The aftermath can be spectacular. A merger can create an object that is hotter, more massive, and more luminous than either parent would have been alone. Some unusual transients, called red novae, are thought to be the visible glow of stars merging in real time. For a brief period, the sky shows the act itself, not just the remade result. These events reveal that stellar evolution is not always a lonely path. Sometimes, two histories collide and the universe writes a completely new one. Some stellar remnants spin hundreds of times in a single second. Among the fastest objects in the cosmos are millisecond pulsars, neutron stars that rotate with astonishing speed and precision. Many seem to have been recycled. A companion star fed matter onto the neutron star over long periods, and that inflowing material transferred angular momentum, winding the remnant up like a cosmic flywheel. By the time the feeding slowed or stopped, the neutron star had become a rapid rotator of extraordinary stability. Imagine something with more mass than the Sun, compressed into city size, turning hundreds of times every second without flying apart. These objects are important not only because they are fast, but because they become exquisite tools. Their pulses arrive with such regularity that astronomers can use them to test gravity, study binary motion, and even search for deep background waves in space-time. Stellar death, given time and companionship, can become astonishingly elegant. Certain stars live fast enough to rewrite themselves in human history. Most stellar evolution unfolds far too slowly for a person to notice. Rare stars break that rule. Some have changed so dramatically over decades or centuries that their stories can be traced across written records, photographs, and modern instruments. Eta Carinae is the classic case, erupting so strongly in the 19th century that it transformed its appearance within human memory. Other unstable stars have shifted temperature, brightness, or spectral type on timescales that let astronomers compare generations of observations and watch the changes accumulate. A star can brighten, dim, shed material, or alter its outer layers in a time span that fits inside archives and observatories, rather than only in theory. These are not frozen points of light. They are ongoing events. They remind us that the sky is not merely ancient. Parts of it are moving quickly enough for humanity to witness the rewrite. There are stellar pairs so close that their outer layers meet and mingle, forming what is known as a contact binary. Instead of two clearly separate spheres, the system resembles a shared structure with matter flowing and stretching between them. The stars orbit each other with astonishing speed, sometimes completing a full circuit in less than a day. Their mutual gravity distorts them into egg-like shapes, and their light changes rhythmically as they eclipse and present different faces to Earth. These systems are fascinating because closeness becomes the defining force. Heat can move between the stars, mass can shift, angular momentum can change the future for both objects at once. In some cases, the orbit may shrink further until the pair merges into a single star. What begins as a duet may end as one remade object. A contact binary is a vivid lesson that in astronomy, intimacy is not sentimental, it is structural, unstable, and often fate deciding itself in public. Black widow pulsars slowly strip and scorch their tiny companions. This is one of the most ruthless relationships in the sky. A black widow pulsar is a fast-spinning neutron star paired with a much smaller companion that is slowly being destroyed. The pulsar blasts out radiation and a fierce wind of particles, heating the little star until its outer layers begin to stream away. Over time, the companion can be whittled down to a mere fraction of the sun's mass. In some systems, it may vanish almost completely, leaving the pulsar alone after consuming the evidence of the partnership that reshaped it. These objects are thought to begin as X-ray binaries, where the neutron star is spun up by stolen gas. Once the feeding phase ends, the pulsar turns on like a weapon. What was once a source of nourishment becomes the target. It is a grim and fascinating inversion, a stellar survivor finishing the work by eroding the neighbor that once helped revive it. In these systems, the compact star is a white dwarf, and the fuel comes from a nearby companion that has wandered too close to its gravitational grip. Gas spills away and forms a bright accretion disk around the white dwarf, circling faster and faster as it spirals inward. For a while, the system may glow with a kind of unstable calm. Then, the disk can suddenly change state, dumping extra material inward and causing a dramatic rise in brightness. The whole system flares, sometimes many times over, before settling back again. These outbursts are not random fireworks. They are the visible result of matter piling up, heating, and surging through a delicate disk that cannot stay balanced forever. The star itself is not newly alive. It is an old remnant made spectacular by what falls onto it. Stolen gas becomes light, and instability becomes theater. A white dwarf is usually the cooling remnant of an ordinary star, stable in its compact form and destined for a long fade into darkness. Yet under the right conditions, it can be pushed toward catastrophe. If a nearby companion feeds it enough matter, the white dwarf's mass can creep upward toward a critical limit. At that point, pressure and temperature deep inside can trigger runaway carbon fusion. Because the star is supported by quantum pressure rather than ordinary expansion, it cannot regulate the reaction in the usual way. The result is sudden and devastating. The entire object can be torn apart in a thermonuclear supernova, leaving no white dwarf behind at all. For a brief time, it may outshine a whole galaxy. These explosions seed space with heavy elements and serve as distance markers across the cosmos. A seemingly quiet stellar ember, given too much from a neighbor, can become one of the brightest deaths in nature. Recurrent novae erupt again and again, instead of only once. In these binary systems, a white dwarf keeps trying to arrest in some of the cities and phenons. The material builds up on the surface until pressure and heat ignite it in a runaway thermonuclear flash. The blast throws matter outward and makes the system brighten dramatically, but crucially, the white dwarf survives. Then, the process begins again. The cycle can repeat over years, decades, or longer, depending on how quickly the fuel returns. That repetition gives these stars a special fascination. They are not one-time accidents. They are systems locked into an unstable rhythm of accumulation and release. Each eruption is both an ending and a promise of another. Watching one is like seeing a fuse relit in slow motion. The star is not destroyed, it is reset, poised to flare again when its borrowed surface becomes too crowded with fuel. Some of the most powerful stellar systems would look disappointingly ordinary if we relied only on human vision. Their real brilliance lies in X-rays, a form of light far too energetic for our eyes to detect. In an X-ray binary, a neutron star or black hole pulls gas from a companion. As that matter spirals inward, it is heated to extraordinary temperatures, hot enough to glow in X-rays rather than visible light. That means the system's most dramatic story is hidden unless we bring the right instruments. Once we do, an entirely different universe appears. The compact object reveals itself not by surface glow, but by the fury of falling matter. Some of these binaries flicker, pulse, or erupt. Others remain persistent beacons. A star that seems unremarkable in the night sky may, in the unseen X-ray universe, be one of the most violent and luminous systems in its region. I hope you can download the book by saying my insensible words. Some stars are known mainly by the wreckage they leave behind. There are times when the star itself is gone or nearly invisible, yet its aftermath still dominates the sky. Supernova remnants are the great examples. An exploded star can leave behind expanding filaments, glowing shells, and tangled clouds of shocked gas that remain visible for thousands of years. The Crab Nebula is a famous case, still expanding from a supernova recorded by human observers merely 1,000 years ago. The star's death threw matter into space and left behind a scene so vivid that the aftermath became more famous than the original star ever was. These remnants preserve motion, chemistry, and energy from the explosion. They are cosmic crime scenes that remain open for ages. Astronomers read them like detectives, using the debris to reconstruct a vanished stellar life. Population 3 stars, if found, would be relics from cosmic dawn. These are the legendary missing elders of astronomy, the first-generation stars thought to have formed after the universe cooled enough for gravity to gather pristine gas. At that time, there were almost no heavy elements, only the simplest ingredients left from the Big Bang, mostly hydrogen and helium. Population 3 stars had none of the carbon, oxygen, and iron that later generations inherited from earlier stellar deaths. Many models suggest they were extremely massive and short-lived, blazing brightly before exploding and enriching the unit for everything that followed. A rosy mass caused gloom and balloon cells to take others from the brain. If one were found directly, it would be like opening a window onto the first great chapter of starlight. These stars are fascinating not because we know them well, but because they stand at the threshold between a dark universe and a luminous one. No one has yet confirmed the universe's very first stars. They remain among the most elusive objects in all of science. Most stars remain bound to the Milky Way, moving in orbits shaped by the galaxy's total gravity. Hypervelocity stars are different. They travel so fast that they can break free entirely and head outward into intergalactic space. Their origin makes them even more remarkable. The leading explanation involves the supermassive black hole at the center of our galaxy. If a binary star strays too close, the pair can be torn apart. One star may be captured while the other is flung away at tremendous speed, like a stone from a cosmic sling. The result is a stellar exile, launched on a one-way trip out of the Milky Way. These stars are beautiful because they turn gravity into drama on the grandest scale. A quiet, sun-like object can become a runaway not through its own behavior, but because it wandered too near one of the most dangerous places in the galaxy. Others were hurled away when their partners exploded beside them. Not every runaway star needs a black hole to explain its speed. Sometimes the cause is more intimate and more sudden. In a binary system, two stars orbit a common center, each bound to the other's gravity. If one of them explodes as a supernova, that balance can be shattered in an instant. The system loses mass, receives an asymmetric kick, or both. The surviving companion, no longer anchored by the old orbit, can be flung outward through space at high speed. What was once an ordinary member of a pair becomes a solitary traveler, carrying the memory of a catastrophe. This mechanism is especially striking because it turns companionship into launch force. The star's speed is not self-made, it is inherited from an orbit that was violently broken. In some cases, astronomers can even trace a runaway star's motion back toward a remnant or a star-forming region, reconstructing the moment its partner died and sent it hurtling away. Subdwarf stars are tiny, hot survivors stripped by close companions. These stars are hotter than many ordinary stars, yet much smaller and less luminous than a normal giant would be at the same temperature. That odd combination comes from a violent loss of outer layers. A close companion can strip away most of a red giant's hydrogen envelope before the star finishes its usual evolution, leaving behind a compact core still burning helium. The result is a hot subdwarf, a stellar survivor caught in a stage that is both exposed and abbreviated. They often appear in binary systems because companionship is the most efficient sculptor of this outcome. What makes them so compelling is how much they compress into one object. You have the heat of a deeper layer, the size of something much smaller, and the biography of a star whose future was rewritten by proximity. A hot subdwarf is not simply a faint blue point. It is a stripped life still burning against expectation. One of the most elegant reasons a star can vary in brightness comes from a kind of stellar heat. Bar is made in bar or bar. In certain zones, gas can become more opaque as it is compressed, meaning heat gets trapped for a while instead of escaping easily. Pressure builds, the layer expands, the gas becomes more transparent, and the trapped energy finally leaks out. Then the layer cools and contracts, setting up the cycle again. This repeating process drives pulsations in several important types of variable stars. The star brightens and dims not because something blocks our view, but because its own outer layers are breathing in response to trapped heat and released pressure. It is a beautiful example of physics becoming rhythm. A pulsating star is not flickering randomly. It is keeping time with its own structure. Just as earthquakes reveal the layered structure of Earth, starquakes allow astronomers to probe the inside of stars by studying tiny oscillations on their surfaces. These vibrations may be driven by pressure waves, gravity waves, rotation, or internal structure, and they leave subtle fingerprints in the light. By measuring those patterns carefully, astronomers can infer a star's mass, age, density profile, and even details about its core. This field, called asteroseismology, turns brightness changes into a kind of diagnostic music. The star does not need to erupt or explode to become revealing. A faint tremble is enough. When that signal is decoded, we are no longer just looking at a shining surface. We are listening to the architecture of a star from the inside out. White dwarfs can crystallize as they cool, becoming cosmic solids. After a white dwarf has spent ages radiating away its heat, something extraordinary can begin to happen deep inside it. The ions in its dense interior slow down enough to arrange themselves into an ordered lattice rather than remaining in a hot fluid state. In other words, the heart of the dead star begins to crystallize. This is not crystal in the everyday sense of a gemstone catching sunlight. It is matter under immense density, packed into a rigid structure inside an Earth-sized remnant. The process happens gradually over billions of years, and it changes how the star cools, releasing heat as the interior freezes, which means the star lingers warmer than it otherwise would. A stellar ember can spend unthinkable ages transforming into a giant solid sphere. It is one of the strangest endings an ordinary star can have. Carbon and oxygen white dwarfs are stellar embers made of fused ash. When a sun-like star reaches the end of its normal life, it does not leave behind hydrogen as its final signature. By then, the inner story has moved much deeper. Over time, helium fusion in the interior has built up carbon and oxygen, and when the outer layers are shed, those products remain as the compact remnant. Many white dwarfs are essentially made of the ash from earlier nuclear burning. These are the leftovers from a long internal furnace, compressed into an object no larger than a planet. Their surfaces may wear thin atmospheres of hydrogen or helium, yet the deeper body is mostly carbon and oxygen packed at extraordinary density. A star that once shone by fusion ends as a hidden archive of what it forged, an ember of transformed matter, preserving the record of the stellar fire that came before. Some stellar courses are so faint they take billions of years to fade. White dwarfs are patient objects. Once the nuclear engine is gone, they do not burn their way onward into a new bright phase. They simply radiate stored heat and cool slowly and relentlessly over immense stretches of cosmic time. That process is so gradual that the universe is not yet old enough for any white dwarf to have fully faded into a cold, dark remnant. In that sense, every white dwarf ever formed is still partway through its long descent. These remnants begin intensely hot, then dim over billions of years until they become faint and difficult to detect. Entire continents can rise and vanish on Earth in the time it takes one of these objects to cool significantly. Death for some stars is not a single event, but a nearly endless twilight. Neutron stars can have mountains smaller than grains on a globe on Earth. A mountain is something vast, towering, and easy to picture. On a neutron star, the same word becomes almost absurd. The gravity at the surface is so intense that matter is squeezed brutally flat. The crust can support only the tiniest deformations before the immense pull overwhelms them. That means a feature that counts as a mountain on a neutron star may be no taller than a fraction of a millimeter in human terms. Scaled to the size of the whole object, it is almost nothing, like a tiny roughness on a polished sphere. And yet, that tiny bump matters. Because the star can spin rapidly, even a minuscule asymmetry can influence the way it moves and radiates. Physical language still applies, but the meanings are transformed by extremity. A mountain can become microscopic and still count as one of the most consequential landforms in the universe. If a neutron star were perfectly symmetrical, its rapid rotation would be elegant but quieter in a certain sense. Add even a tiny, persistent dump, and the story changes. As the star spins, that unevenness means the mass is not distributed with perfect balance, and according to general relativity, an accelerating asymmetry can radiate gravitational waves. These are ripples in space-time itself, faint and difficult to detect, but real. A distortion, tiny by everyday standards, carried on an object as dense and fast as a neutron star, may be enough to send those ripples outward across the cosmos. Scientists search for such continuous signals because they would reveal not a violent collision, but an ongoing imperfection turning steadily in space. A dead star, nearly perfect, yet not quite, and because of that tiny flaw, the fabric of the universe shivers in rhythm with its spin. Magnetars can unleash giant flares strong enough to affect Earth's atmosphere. When a magnetar suffers a sudden rearrangement in its magnetic field or crust, it can release an enormous burst of high-energy radiation called a giant flare. These are among the most violent flashes known from any star-sized object. One famous event in 2004 was so powerful that it briefly disturbed Earth's atmosphere, even though the source lay tens of thousands of light-years away. A dead star in another part of the galaxy released enough energy in a moment to leave a measurable fingerprint here. The flare likely came from a catastrophic magnetic adjustment, a kind of stellar convulsion in an object already living under impossible tension. For a fraction of a second, the magnetar became one of the brightest high-energy sources in the sky. It is a reminder that even a remote corpse can still reach us. End of public. Some magnetars also behave like radio pulses, blurring old categories. For a time, magnetars and radio pulses seemed like separate classes. One group was defined by extreme magnetic activity and high-energy outbursts. The other was known for regular beams of radio emission from spinning neutron stars. Then observations revealed objects that did both. Some magnetars were caught producing radio pulses, while certain pulsars showed hints of magnetar-like behavior. Suddenly, the boundaries looked less like walls and more like regions in a larger landscape of neutron star possibilities. A neutron star can move through different behaviors as its field, rotation, and environment evolve. What once looked like separate species may be related expressions of the same deep physics. This is one reason rare stars are so valuable. They expose where classification starts to wobble and where the real universe turns out to be more continuous and inventive than our names for it. Rare stars often matter most because they test impossible physics. An ordinary laboratory is limited by budget, safety, engineering, and the laws of matter under human-scale conditions. Rare stars ignore those limits completely. They create densities, temperatures, magnetic fields, and gravitational regimes that no machine on Earth can sustain. That makes them more than curiosities. They become experiments already running in the universe, waiting for us to interpret the results. White dwarfs test quantum pressure. Neutron stars probe ultra-dense matter. Magnetars confront us with impossible magnetism. Pulsars let us test timing and relativity with extraordinary precision. These stars carry physics into places where equations are no longer comfortable, and then they send signals back across space. When astronomers study them, they are asking nature how matter, light, gravity, and time behave under extremes no earthly apparatus can match. Rare stars are where theory goes to be challenged. They turn the night sky into a laboratory beyond Earth. Under Romanism, blood stars, or mass stars, can sculpt enormous bubbles in surrounding gas. A Wolf-Rayet star does not simply shine into space, it attacks space. Its wind rushes outward at astonishing speed, slamming into the surrounding gas and sweeping it into vast shells and cavities. Over time, that pressure can hollow out enormous bubbles in the interstellar medium, like a storm carving an empty chamber in a cloud. These structures can stretch across many light years, glowing where shock waves heat the gas and trigger new patterns of light. What makes this so captivating is the scale of influence. One star can alter an entire region around it, not by exploding, but by living violently enough. The star becomes an architect of emptiness, pushing matter aside and tracing its presence in enormous curved walls. When astronomers image these bubbles, they are seeing the reach of a rare star made visible, a portrait painted not by light alone, but by wind, pressure, and relentless stellar force. Some are wrapped in pinwheel dust, spirals made by binary winds. In a few rare binary systems, two fierce stellar winds collide and create something almost too graceful for such violent origins. One star may be a Wolf-Rayet object rich in carbon, while the companion drives a powerful wind of its own. Where those winds crash together, the gas can cool enough for dust to form. Then, the orbital motion of the pair winds that fresh dust outward into a spiral. The result is a glowing pinwheel pattern turning through space, delicate in appearance, and born from collision. Every turn of the orbit writes another loop into the spiral, and the structure expands as a record of time itself. Instead of chaos looking chaotic, it becomes ordered by motion. Even some of the harshest stars can produce shapes of eerie elegance when companionship and wind conspire just right. WR-124 is a doomed giant blowing off its future shroud. This star is a spectacular example of a massive object already preparing the seam for its own end. WR124 sits inside a glowing nebula of material that it expelled through fierce stellar winds, building a cocoon around itself while it still lives. The surrounding cloud looks almost like a future ghost, waiting in advance. The star at the center is unstable, hot, and short-lived on cosmic timescales, the kind of object astronomers study because it shows a massive star in a late and revealing phase. What you see is not merely a star and not merely a nebula. It is a relationship between the two, the central engine and the future shroud it has made from its own body. Few sights capture impending stellar ruin with such grandeur. Some Wolf-Rayet stars may be moments away from supernova on cosmic timescales. In human terms, these stars are ancient and impossibly distant. In cosmic terms, some may be standing almost at the edge of the trapdoor. A Wolf-Rayet star has already burned through enormous amounts of fuel and shed much of its outer mass, revealing layers that belong to a late chapter of stellar evolution. That means when astronomers observe one, they may be seeing an object that has only a tiny fraction of its lifespan left. Tiny, in this case, may still mean thousands or hundreds of thousands of years, long to us, but a final breath to a massive star. They are not merely unusual stars, they are candidates for catastrophe already underway. Every fierce wind and exposed layer hints that the core is racing through its remaining options. One day, the balance will fail, and the star may disappear in a blast that had been silently approaching the whole time. Andrew Webster prays matter. These stars expose fusion layers. Ordinary stars keep hidden inside. Most stars guard their internal chemistry beneath thick outer envelopes, so we see only the surface, not the deeper layers where the real transformation happens. Wolf-Rayet stars break that rule. Their ferocious mass loss strips away the usual covering and exposes regions enriched by advanced fusion. That means astronomers can detect unusual surface abundances of elements like helium, nitrogen, carbon, or oxygen, depending on which layer has been uncovered. In effect, the star has turned part of its interior outward. This lets us study a stage of stellar processing that is normally buried and inaccessible. The star becomes a living cutaway diagram of itself. It is one thing to know that fusion builds new elements in deep stellar furnaces. It is another to see a star whose violent history has peeled back the surface and made those inner chapters directly visible. Usually we imagine loss as simplification. In stellar evolution, loss can create the opposite. A massive star that sheds its outer layers may reveal behaviors, chemistry, and structures far more exotic than it showed in its fuller youth. While wrapped in hydrogen, it might have looked relatively ordinary for a giant star. Strip that envelope away through winds or binary interaction, and suddenly deeper fusion products appear, new instabilities emerge, and the star enters categories that feel increasingly bizarre. The object becomes hotter, more compact in some ways, and more informative to astronomers, all because it has less of itself left. The closer such a star comes to destruction, the more revealing it becomes. Layers vanish, secrets emerge. In the universe, losing substance can sometimes mean gaining identity. Blue stragglers may form when stars collide in crowded clusters. In the packed interiors of ancient star clusters, gravity can bring stars into surprisingly intimate encounters. When two stars merge, the result can be a single rejuvenated object with more mass and fresh hydrogen available for burning. That new star shines hotter and bluer than the older cluster population around it, standing out as a kind of youth fraud inside a stellar retirement home. This formation route turns crowding into creation. The cluster is not merely a collection of old stars aging together. It becomes a place where proximity can rewrite destiny. A collision is usually imagined as destruction, yet here it can produce a star that looks renewed. In a cluster where most bright stars should have faded long ago, a merger can create a fresh imposter and make the old population look suddenly less settled. They can also form when one star quietly drains another. Not every blue straggler needs a dramatic crash. Some may be built through a slower and more secretive kind of theft. In a binary system, one star can evolve and expand until its gas begins to flow toward the companion. If enough mass is transferred, the receiving star becomes heavier, hotter, and bluer than it would have been on its own. To an outside observer in the cluster, it can look oddly youthful compared with neighboring stars of the same age. This route is fascinating because it is less explosive and more intimate. The transformation happens through quiet imbalance, one star fading while the other is refreshed. In some cases, the donor is eventually reduced to a faint remnant, leaving the brightened star looking almost innocent, unless astronomers search carefully for clues. Sometimes stellar deception comes not from violence, but from long partnership and unequal exchange. We like to think stars advertise their stage of life honestly through color, brightness, and temperature. Rare stars often undermine that assumption. A merger can create an apparently youthful object from old ingredients. Mass transfer can refresh a companion and make it look younger than the system it belongs to. A stripped star can appear unexpectedly hot because its deeper layers are exposed. In all these cases, the visible properties hinted one age or one pathway, while the true history lies elsewhere. That makes rare stars especially seductive and frustrating. They tempt us with surface clues, then punish us for trusting them too quickly. For astronomers, this is not merely a nuisance. It is an invitation to investigate more deeply. The star becomes a false passport in the archive of the sky. It presents one identity and carries another. A star's composition is not merely a list of elements. It can be a historical record. If deeper layers have been exposed, the surface may show products of fusion that do not belong in an untouched outer atmosphere. If a star has accreted matter from a companion, certain abundance anomalies may linger as evidence of that exchange. If two stars merged, the new object may carry a chemical pattern that does not fit ordinary single-star evolution. This is one of the great powers of stellar spectroscopy. The chemistry is not only what the star is made of now, it is a trace of what has happened to it. A violent loss, a quiet theft, or a buried merger may leave no visible scar in shape, yet the atoms remain talkative. They remember the history even when the surface tries to pass as innocent. Some red giants pulse so deeply their brightness rises like breathing. Near the end of a modest star's life, the outer layers can become so swollen and unstable that the whole star begins to expand and contract in slow, powerful cycles. The effect is not a tiny shimmer. It can be a broad, heaving change in size, temperature, and light, as though the star is breathing across space. These pulsations happen because gravity and pressure keep falling out of step with one another in the giant envelope. As the outer layers expand, they cool and dim. As they contract, they heat and brighten again. We are not talking about weather on a star. We are talking about the entire visible body of the star moving inward and outward over weeks or months. A red giant in this state feels less like a fixed sun and more like a living ribbon. Even very old stars can still move with surprising grandeur before they finally fade. Mirror variables are old red giants whose brightness rises and falls over long, regular cycles, often lasting many months. At their brightest, they can become dramatically more visible. At their faintest, they may almost disappear from ordinary view. The star mirror itself astonished early skywatchers because it seemed to vanish and return, earning a name that means wonderful. The reason lies in powerful pulsation. The star's outer layers grow and shrink in a repeating cycle, changing both its size and temperature. Because these stars are so cool, even modest temperature shifts can have huge effect on the visible light they emit. A star is not switching on and off, it is slowly breathing and changing color in a way that transforms its apparent brightness. Nearer variables make the sky feel patient, rhythmic, and deeply alive. Astronomy lets astronomers listen to stars instead of only seeing them. A star can look calm from a distance and still be ringing with hidden motion. Tiny waves move through its interior, rise to the surface, and cause slight changes in brightness or motion that sensitive telescopes can measure. Astronomers study those patterns much the way a musician might study the tone of an instrument. A large hollow object sounds different from a dense compact one, and a star follows the same principle. Its oscillations carry information about age, internal layering, rotation, and the size of the core. This is why astroseismology feels so remarkable. It turns starlight into structure. Instead of guessing what lies beneath the surface, scientists can infer it from the star's own vibrations. The method has transformed ordinary points of light into objects with readable interiors. A star no longer needs to explode to reveal itself. Sometimes all it has to do is tremble, and the universe suddenly becomes far less silent. The sky contains stars that beat, flare, fade, and erupt. It is easy to imagine the stars as fixed lights, distant and unchanging, because to the naked eye, most of them seem exactly that. Yet once astronomy began watching carefully and repeatedly, the sky transformed into a place of motion. Some stars pulse with slow, regular rhythm, others flash in violent bursts. Some fade behind dust they create themselves. Others erupt through mass loss, collapse, or unstable accretion. The night sky turned out not to be a frozen pattern, but a vast field of ongoing behavior. A star is not just a point. It can be a clock, a warning, a flare, a disguise, or the aftermath of some older collision. Each kind of change reveals a different layer of physics and history. Once you understand that, the heavens stop feeling static and start feeling active. The stars are not merely present above us, they are doing things. Some stellar oddities are seen only because modern telescopes arrived in time. For most of human history, the sky was observed with eyes, memory, and patience. That was enough to notice bright novae, mere as changing light, or a great supernova. But many rare stellar behaviors are subtler, shorter-lived, or hidden in wavelengths human eyes cannot detect. Modern telescopes changed that completely. Space observatories revealed X-ray binaries and gamma flares. Infrared instruments exposed dust-shrouded stars and pinwheel spirals. Wide-field surveys began revisiting the same sky night after night, catching transient outbursts that older astronomy would almost certainly have missed. Some rare stars were always there, performing their strange acts in silence, while humanity lacked the senses to notice. The modern era did not create those objects. It simply arrived with better eyes, just in time to see their hidden performances. A rare star can teach more than a million ordinary ones. There is great value in the ordinary. Most stars are useful because they establish patterns, anchor theory, and show the common ways stellar life unfolds. But every so often, one rare object reveals a weakness in our understanding so sharply that it teaches more than countless routine examples combined. That is because science advances most dramatically where expectation fails. A single magnetar flare can challenge models of magnetic stress. One stripped binary can clarify how stars exchange mass. A peculiar pulsar can expose missing details in our picture of stellar interiors. Rare stars matter not because they replace the common ones, but because they illuminate the edges of the rulebook. One strange star can redirect whole areas of research by forcing better questions. In astronomy, the exceptions are not ornamental. They are often the places where the deepest learning begins. When we think about stars, we often focus on their formation, the drama of clouds collapsing and new light igniting. Rare stars reveal that endings can be just as generative. A dying massive star may sculpt a nebula, enrich space with heavy elements, and leave behind a neutron star or black hole. A sunlight star may cast off a glowing shell and become a white dwarf that cools into crystalline matter. A binary death spiral can create novae, stripped remnants, or merged objects with new identities. In each case, the final chapters do not simply erase what came before, they produce new forms, new chemistry, and new physical laboratories. Death, in stellar astronomy, is often an act of transformation rather than disappearance. Destruction in the universe can also be a form of creation. The end of one stable state becomes the beginning of a stranger, and often more revealing one. Once you notice rare stars, ordinary starlight never feels ordinary. That may be the most lasting change these objects produce. After learning about pulsars, magnetars, blue stragglers, stripped stars, pinwheel binaries, and crystalline white dwarfs, it becomes impossible to look at the night sky in quite the same way. The stars no longer feel like a single category. Every point of light becomes a possible history. Some may be stable and familiar. Others may be hiding companions, shedding matter, pulsing in silence, or carrying the aftermath of some long-past collision. Rare stars do not only make the strange ones more fascinating, they deepen the entire sky. They turn starlight into biography, physics, and possibility all at once. Once that shift happens, the heavens stop looking like a backdrop. They become a crowd of stories, and even the calmest light begins to feel charged with hidden drama. Closing tonight, we wandered among some of the strangest stars the universe has ever made. We passed through clouds shaped by stellar winds, through spirals of dust turning around hidden companions, through stars that pulse, flare, steal, collide, and slowly transform into something far stranger than the steady lights we usually imagine. We visited dense remnants where matter is crushed beyond reason, magnetic stars that can lash out across the galaxy, and ancient imposters hiding in old clusters with borrowed youth still glowing on their surfaces. And now, after all of that distance and fire, perhaps the sky feels a little different. Not empty, not silent, but full of lives unfolding in darkness, some brief and brilliant, some slow and fading, some hidden beneath dust or folded inside binary systems or waiting at the edge of an ending that will one day reshape everything around them. So now, let all of that begin to drift. Let the strange stars grow softer in your mind. Let the bright remnants dim into the background. Let the spirals, the pulses, the flares, and the fading lights settle into a calm and distant glow. If you enjoyed this journey, you might like to subscribe, leave a thought below, or return for another sleepy exploration soon. But for now, just rest. Let your breathing slow. Let your body grow heavy. And let the last of these faraway stars fade gently above you until there is nothing left to do and nowhere left to go but sleep. Sleep well, and good night.